Okay, thank you. I'm honored to be presenting here. My topic is non-volatile switching of nonlinear Hall effect in topological insulator, crystalline insulator at room temperature. Okay, so Berry curvature is often referred as a fictitious magnetic field in momentum space. Recently, Berry curvature dipole has been proposed by Solomon and Ganfu, which is basically a total derivative of Berry curvature in momentum space. So this describes non-equilibrium distribution of Berry curvature, and this can have non-zero value when inversion symmetry of the material is broken. So at the presence of Berry curvature dipole, BCD, you can expect current-induced magnetization and a nonlinear Hall effect in this material. So I'd like to now explain how nonlinear Hall effect and what is occurs and what is it. When the material has Berry curvature dipole, and when you apply charge current along Berry curvature dipole direction, it can actually induce magnetization out of plane one, which has linear relationships to D and I. And of course, now we have out of plane magnetization and the current. You can also expect Hall voltage, which is proportional to the M and I. But this M is actually linear to current. So what we expect, what the expected nonlinear Hall voltage is actually linear to the square of current. So you can expect this kind of parabolic signal on the current. So actually this effect has been observed from transition metal dichalcogenides and more graphenes. And also modulation of this effect has been demonstrated by electric field gating and strain control. They observed the changing amplitude and also changing sign of the nonlinear Hall voltage and the Berry curvature dipole signals. But what's unexplored yet is non-volatile switching of Berry curvature dipole. If we can achieve non-volatile behavior of Berry curvature dipole switching, what we expect is this kind of hysteresis behavior on the external control field. So we set the goal of our study to realize switchable and non-volatile Berry curvature dipole. In other words, it can be called the ferroic Berry curvature dipole. So to achieve this goal, we focused on the material called topological crystalline insulator, especially lead tin telluride. It has 4 Dirac cones on its first brilliant zone. And also one interesting point of this material is it has a ferroelectricity. Yeah. So here I'd like to explain how this material can have Berry curvature dipole. This is the image of the atoms on the 001 surface. There are 2 mirror planes, and each mirror planes protect 2 Dirac points. And if there's ferroelectric distortion of atoms take place, one of the mirror plane is broken. So actually the inversion symmetry of the system is broken in this case. And accordingly, 2 of 4 Dirac points opens up gaps, and they can obtain finite Berry curvature. And because their signs are opposite, we can expect Berry curvature dipole along this axis. And this Berry curvature dipole is directly related to ferroelectric distortion, so we can expect ferroic motion of Berry curvature dipole from this material. And this is the material we grew. And from TM, R-heat, and XRD, we confirmed this is a single crystal, and the composition ratio of lead and tin are 48 and 42%. And we doped a little bit of antimony to compensate the vacancies of tin and lead. And this is the resistivity versus temperature result. As temperature decreasing, resistivity increased, and at this point, the resistivity almost saturated. This is a kind of a typical behavior in topological insulators. And this is the experimental setup for nonlinear Hall effect measurement. We applied AC current along y-axis, and we detected transversal second harmonic voltage along x-axis. And this is a result. From lead tinted light, we successfully observed the parabolic behavior, which is a typical characteristic of nonlinear Hall effect. And from lead tail light material, this is not topological crystalline insulator. This is a trivial usual semiconductor material. We didn't observe nonlinear Hall effect. So because we observed nonlinear Hall effect from lead tinted light, we found a very curvature dipole in this material. And as temperature decreases, the amplitude of nonlinear Hall voltage increases rapidly. This shows the effect is actually occurring at the surface state of the topological crystalline insulator, because at low temperature, bulk carriers are suppressed. Yeah, so we actually observed this effect. So now next, our target is to switch this behavior. So we did same measurement after applying a pulse electric field to the material. By applying pulse electric field from positive and negative x-axis, what we found is clear switching of nonlinear Hall voltage. This can be easily explained by the ferroelectric distortion of the material. By switching the ferroelectric distortion by electric field, pulse electric field, the direction of Berry curvature dipole is reversed, so that the nonlinear Hall voltage direction also reversed. So what happens when we apply pulse electric field along y direction? In this case, ferroelectric distortion takes place along y direction, so Berry curvature dipole is in x direction. But applied electric field is in y direction, so that their cross product is zero, so there's no nonlinear Hall voltage. So we successfully controlled Berry curvature dipole by pulse electric field. So finally, we swept the magnitude of pulse electric field, and then it showed clear hysteresis behavior of nonlinear Hall voltage. So it indicates successful demonstration of ferroic Berry curvature dipole, even at room temperature. And at last, we calculated the magnitude of Berry curvature dipole, and it was around 150 nanometer at low temperature and around 86 at room temperature, which is compared with the previous reports, it's relatively large value. And to summarize my talk, we explored ferroic behavior of Berry curvature dipole in topological crystalline insulator, and we observed non-volatile switching of Berry curvature dipole and related nonlinear Hall effect, and we successfully observed hysteresis behavior. And this is already published in Nanoletters, so please find it if you are interested. Thank you.
Thank you for the report. Is there any question from our attendees? Is there any question? Yes, we still have quite some time if anyone wants to discuss with this wonderful work. Is there any question? Okay,
Yeah.
yes.
Okay.
Okay, yes, please.
Okay, hi, am I audible?
Yes.
Yeah, my question is like here the presenter has mentioned 150 nanometer of the largest BCD value. So my question is like only the BCD phenomena happens when you do this measurement, or there is other kind of phenomena also happen like RRKY, or let's say the surface phenomena is also happen like Rasba and all those things. So does we have to do the account for that, like author has done, or maybe presenter has done something like that? Hello.
Yes, I think this video is a little bit lagging. Um, let's wait a minute. Oh, so
Sorry,
Okay.
I couldn't catch your point.
My point is, like, you have mentioned the 150 nanometer, the largest BCD value you have observed, correct? I cannot get whether.
I
Okay.
think it's
Video.
disconnected. Oh yes,
Yeah,
reconnected. Yes.
it's okay, fine.
Oh, can
Now it's okay. We can move to like next. I want to see the next.
Okay.
video.
I'm sorry, my connection was bad.
Oh, okay. We still
But
have
yeah,
a little bit time. Yes.
Okay.
okay.
Can do you want to repeat your question? Or
Yes. The first
Okay.
question. Okay, I will ask in a very simple manner. Like you can consider it's not a very hard answer. It's just I want to understand like how you came up with this thickness number 150 nanometer, and the how do you like consider about the other phenomena which is happening while doing the measurement.
Oh, I see. Okay. Well, actually, this unit of the very curvature dipole has like a dimension of the length, but it's just a unit, so it doesn't mean kind of a thickness or something like that. It's just a unit. So
So this result is a
it's not.
simulated one, correct?
Yes. It's
Okay.
not simulated one. It's a calculated one from
Experiment.
the experimental result. Actually,
Okay.
number from roughly simulated number from other reports are very are like 2 orders smaller than these values. So we are not still sure why this value is such large in our material, and other effects like thermal effect or something like that, right? Into the
Like Rasba effect,
of
like RRKY effect. There are so many effects, but the
yeah.
thickness is so high, like it will nearly considered as a bulk because if you see the previous presenter, I'm doing also study, so they hardly mention about 2 nanometer to up to like 50 nanometer we can think of, but 150 nanometer is such a huge thickness. It will almost like I'm just wondering. It's not like very critical
Okay.
question, but
First 55 nanometer is not the
yeah.
thickness of this material. It's the amplitude of very curvature dipole. It's not like something thickness, or it's not device or
Okay, and
related value.
the
And
other
then
phenomena,
other
the other
phenomena
phenomena
about
is
actually our observation, this
mm,
nonlinear Hall effect switching
mm,
is directly related to the pulse electric field. So if the other phenomena could be if the other phenomena which has contribution to the this kind of nonlinear Hall effect could be there,
mm, mm.
and it's related
Okay.
to the ferroelectric distortion, yes, we should consider. But I didn't find any other effect related to the ferroelectric distortion and this kind of nonlinear transport. So we concluded this phenomena is directly related to very curvature dipole at surface of our material.
Okay.
Do
Thank
I
you.
answer to your question? Okay.
Yes.